Yes, hello everybody. Here I am again with my new video that is based on electric potential. In last lecture I have described about electric field, especially electric field in an electrostatic field. Actually electrostatic is a branch of electromagnetism where charges are in rest, so I described that. Now I'm going to explain electric potential. Let's see what's happened here. I'm not going to explain, I'm not a teacher, I'm a student. I'm explaining what I learned according to my own view. See, here's a charge which is at infinity. This charge wants to travel to this position. That is the first position. Here, the charge is making a travel from Q to Q, from infinity to here. And in a vacuum space, in an empty space, in an empty electromagnetic space, there are no other charges. Only this charge starts its journey from infinity and reaches here. Means there is no any other charge, no any other thing in the environment to disturb it. Means the potential energy is zero. Because the potential energy is an energy which is due to the location, due to the presence of any other resistance, and there is no resistance. At infinity, we take U equals to 0. Potential energy of this charge is equals to 0 at infinity. Because there is nothing to resist or to support or to disturb its existence. And there is no other charges in this environment also. So this charge is making a transition from this place to this place, having U is equals to 0 here too, and U is equals to 0 here too, because there is no resistance. And we have final potential energy here and initial potential energy at infinity for this charge. Now, what done to bring this charge from infinity to point 1 is 0. Why? Final potential energy minus initial potential energy is equals to 0. Because this is also 0 and this is also 0. That's the key point here to notice. But the situation will be not like that. If there's a charge which is to disturb its travel from infinity to this point, let's put a charge plus capital Q, which is different than the magnitude of this Q at this position, which the location of this plus Q is at a distance R from 1. Means the first position of this small q from infinity to this point is at a distance r from this plus q. This time the situation is completely different. We have u is equals to 0 at infinity, because at infinity the effect of this positive charge is almost negligible, and so this charge has still no disturbance, no resistance at infinity. So u is equals to 0 even in this case also, but u is not equal to 0 here in this case, because what? This location, the charge at this location is highly disturbed by the presence of this charge, and thus what then to bring q from infinity to point 1 is not 0 this time, is equals to u first minus u this, and which is perfectly not 0 here, and I'll have to find that. And from here I'm going to explain what I learned for electric potential. Pause it, I'll have to check. Yes, as I discussed here, when there is a presence of plus q here, then incoming of this q from infinity to this point is not like previous one. It work done is also not 0 here. Work done will be u1 minus u infinity, means potential energy at this position minus potential energy at infinity. And as we know, the potential energy at infinity is equals to 0, but this term is not 0 this time, and we'll have to find work done. So let's calculate. Work done to bring this small charge from infinity to this point is equals to difference between its energy at this point and at infinity. That is equals to force into displacement. Let's see here that work done, we know that from mechanics, work done is always force into displacement. And as this charge starts its journey from infinity, at infinity the effect of this q is 0, But as it starts its journey from infinity and heading towards here, this is positive and this is also positive. So they both repel each other. So this force is resisting that charge. And this charge, each and every step of this charge towards this point, to reach at point 1, is opposing the resistive force of plus Q. So I'll have to use that force at a distance, and this is actually the position is not located at one single point during the journey. On each and every step between the point, the force produced by plus Q over Q is changing. So I'll have to use the integral method. That is, for ds, I have written here dr.
Put the vectors on f and ds.
Okay, no, that's not so complicated. So in calculation, see here, this is the dr, q by r squared dr. And someone can ask me, and there are a lot of confusion, someone can ask me that the force is in this direction and the charge is heading towards this. So during the dot product, I need to write here cos 180 degree and that will be minus. So don't go with that. Whenever the one vector and this vector, they both are in this direction from the curvilinear coordinates, we now ds can be written as dr when there is another terms of 0 like this. So ds is transformed here in dr, and this, the dot product, the result of cos 180 degree for force is in this direction and ds is in this direction. That should be done by changing the limits. It's a very good calculation, the way to calculate. We don't have to change the infinitesimal distance, the direction of infinitesimal distance while integration. We should have to keep it alive, along, according to its direction. But for the direction, when f is opposite to ds, we'll have to change the limit.
Of the integration.
F is here and ds is here. So we don't do anything here. We put the value of f and we put ds in terms of dr, because my distance is calculating under the infinitesimal distance dr. But the opposite nature of these two has been shown by the limit. Initially, I know ds is heading towards this. Calculation of ds goes from here r to infinity, but it is opposite, so my integration starts from r to infinity. Understood? That is, initially ds has a calculation, charge is heading towards here, so initial location is infinity and final location is r, but they are opposite to each other. So to calculate such cases, in such cases, we should have to keep f and ds alive according to the magnitude, and we have to do this calculation, this opposite calculation by changing, inverting the limit of dr. Dr is infinity to r, but it is opposite cos 180 degrees, so we integrate from r to infinity, and that gives you the correct result. So there is very less chance of confusion here, and thus I get this, and by solving I get this. So here we now have the work done to bring q from infinity to this point when there is a positive plus q is to disturb the traveling of q, the journey of q. Then we have work done is equals to this. This is a very key point. This work done means a change in potential energy. Means this work done tells us that the potential energy is not same on each and every point now. Initially it's 0 at infinity, and after that it's changing on each and every steps. And at one, the change is so vital that we get this value. But initially when there were no plus q, it is 0. Pause it now.
Start.
See, work done is equals to q by 4 pi epsilon naught r. Means work done to bring this q, small q, from infinity to this position when plus q is present is this. And from here, take a ratio, w by q, work done to bring this charge from infinity to this. This ratio is q by 4 pi epsilon naught r. And if I see this ratio in some broader sense, then I can see that this work done is actually difference between the potential energy from infinity to this location when plus q is present by this, q by this. And this is a change in potential energy from infinity to this location When plus q is present, remember when plus q is present, if there is no plus q, then u here is 0, u here is 0, no work done to bring this charge from here to here anywhere in space. But this time there is plus q, so this and this. This ratio is called electric potential difference between this point to this point. Or you can say work done per unit charge, the charge which is coming, the charge which we are bringing from infinity to the given location, the ratio of that charge to its work done, or the change in potential energy of that charge, of the same charge to the magnitude of charge, is electric potential difference. This is the electric potential difference. And the striking feature of this is that this is going to be constant. Here we can see. See, this ratio is electric potential difference between infinity to this point. And what are you noticing? This is q by 4 pi epsilon naught r. It is not dependent on this distance. It is dependent on this distance. So whatever be your journey, suppose we are making a journey like this. We are making a journey through this way. After all, it's constant. So it is clear the electric potential difference is independent of the path used by the charge which is traveling from one position to another position. So it is free from the path. Understood? Pause it now.
Go.
See, this work done per unit charge which is coming from infinity to point 1, or the change in its potential energy from infinity to point 1 by q is electric potential difference. We discussed it. Convert this value into u. Potential energy at this point minus potential energy at this point by q is equals to EPD. I have written it in short form. Or this ui by q minus, and as we know that u at infinity for any situation, if there is plus q present or not, after all this is equals to 0. So only this term survives here, and that is EPD. That is the value should be, the value will be this. This ratio, see here, when the potential energy at other point or at infinity becomes 0, in that case, the potential energy, the ratio of this potential energy at this point with respect to magnitude of the charge which is coming from infinity to that point is VI. And this value is considered as electric potential at point 1. At point 1. Means electric potential is just the electric potential difference between 2 points. When the electric potential energy at other point will be 0. In that case, potential difference is considered to be potential at that point. That is this. Means electric potential means to a reference point always. Means there is no electric potential. Actually, it's electric potential difference between 2 points. Energy of this point to this point. But if the energy is 0 here, so due to the presence of this, only the energy here is meaningful. And so we say sometimes that electric potential difference whenever energy at infinity is 0 is not electric potential difference, but we say simply electric potential at I. Electric potential is just the potential difference. Understood? It has always meaning with the reference point. In this case, the reference point is at infinity, from where the charge starts its journey. Stop it.
Stop.
See now, we have studied about electric potential difference and electric potential of a point charge at a distance r. But this time, feel it. What is electric potential? From infinity, a charge is traveling. There are 3 points located here, and the presence of plus q is here. The first location is at a distance r1 plus q. Second is at a distance r2 from plus q, and third is at a distance r3 from plus q. Q starts its journey from infinity and come here.
The infinity is not visible.
It's not visible.
It's on the spot.
Q is also on a spot. As we know, the potential difference is equals to difference in the potential energy at the locations where this charge is traveling, and ratio to this to the magnitude of this charge. See here, for the potential difference between first point to infinity, Vi minus V infinity is equals to potential energy at first point minus potential energy at infinity in the presence of plus Q by this small q. That it is because this is 0 and we get this. Similarly, for second point we get this, and distance of second point from plus Q is R2. Distance of third point from plus Q is R3. And this, I get the potential differences between the first point to infinity, second point to infinity, and third point to infinity will be these three respectively. Now we can see.
Wait.
So you can see here the potential difference between first point to infinity, second point to infinity, third point to infinity, having these values respectively. And as we know, the R3 is smaller than R2 and R2 is smaller than R1. So we can say that potential difference is higher at third with respect to infinity, then second with respect to infinity, and then first to infinity. So, and as we know, potential energy at infinity is equals to 0. So potential difference at infinity, value potential at infinity is also 0. So these values are, I remove these values. And now what it's giving? The potential at this point, potential at this point, potential at this point in the presence of plus Q. Remember, these are not the potential, electric potential. These are the electric potential difference of these 3 points with respect to this point in the presence of plus Q. Okay, so we can say, because the U is equals to 0 here, so we can say it as electric potential. What are you seeing here? Means U3 is smaller, is greater than U2, is greater than U1 here. Means once this charge starts traveling from here towards the plus Q, it requires a definite amount of energy to each and every places in the path. And each and every places in its path requires some particular amount of potential energy for this Q to pass through that point. If this Q has not that much energy to pass through this point, then it will not pass through that point. It will stop. That's the potential. Ratio of that potential energy, which is required by this Q, to the magnitude of this Q is the potential. And you can see for this Q, the energy required at this point to pass through this point or to reach to that point is UI. And that value is some particular value. Similarly, a small q had to pass from second point or to reach to this point in the presence of plus q requires u2, this amount of energy. And similar to this, and similarly on each and every step, every point throughout its journey, a small q requires some amount of energy pass through that point. If Q has energy less than that, it cannot pass through that point towards Q. That's the electric potential energy. And when I take the ratio of that energy to the magnitude of charge, it gives us potential, electric potential. And if I take the ratio of that potential energy to this charge at two different locations, one here and one here, then that is electric potential difference. So electric potential at any point tells us that this charge requires some particular value of energy. This value says us that U to Q, that you require this amount of energy to pass through this point. If you don't have this amount of energy, you can pass through that point. And what a striking feature for this potential is that this potential is independent of this charge. So if this Q requires this amount of energy to pass this point, then instead of this charge, Q dash requires some different amount of energy to pass this point. But the ratio of this and this again is equals to this. That is independent. Means if the incoming charge changes its magnitude, then the energy required for it to pass through the points also changes, but the ratio is constant. Ratio of the energy required to this charge to pass through this point is constant. It depends only on the presence of this charge. And that's a striking feature for the potential, that it tells that each and every charge, each and every value of charge which starts a journey from one point to another point requires some particular amount of energy to pass through that point or to reach that point. And the ratio of that energy to the magnitude of the charge is constant. If I change here some greater charge, this energy increases. Means for a greater charge to pass through this, which starts a journey from here to pass through this point, requires some greater energy. So energy changes, charge changes, but the ratio is still this through this point. That's the striking feature of potential. So potential through that point is constant. Only the potential energy required for the charge to be passing through that point to achieve plus Q will change. Pause it now. As I discussed that the potential is free with the potential energy required at that point by the charge. It's actually the ratio of the potential energy with respect to the charge which is passing through that point. So for Q, suppose my charge is Q here, then the potential difference at this point, or if U is equals to 0 here, in that case, EPD, electric potential difference, is just electric potential of this point. So V at I, sorry, not first, I, it is not I, it is first, is equals to U at first by Q is equals to this. If I'm taking here 3Q, then this will be thrice. If my charge changes from Q to 3Q, then Vi is still this value. So to keep it constant, energy required to pass through that point for this 3Q is also thrice, and this. So, and similarly for each and every point. So change in potential, electric potential difference or electric potential when we have U is equals to 0 at infinity is independent of potential energy required at that point and the magnitude of the charge which is passing through that point, but it is the ratio and it's always independent of these two values. It's constant for what if the situation is not changing. If there's the plus Q is here and at infinity U is equals to 0, then whatever charge starts its journey from here to pass through this point, the charges requires different amount of energy suitable to their product magnitude, but the ratio of this to this, the potential through this is always this. It's not going to change. That's the nature of electric potential of it now. See an analogous example to explain what is actually the electric potential. I have explained it in a very theoretical way, but this time an analogous feeling or mechanical feeling that how it tells us. Suppose there are two components, C1 and C2 are two components. C1 is bigger and C2 is smaller. I mean C1 has more complaints, C2 has less complaint. And they start journey from somewhere at infinity or somewhere to their house to meet the king here and tell the king about their complaint and their problems. This is one gate. There are similar gates in the way. I'm explaining to just one gate. Here's a soldier which is guarding the gate. Now see here, C1 and C2 starts journey from anywhere from their house where they require no amount of money. Now, as they reach here, the soldier is telling to C1 or C2 that you need some tax. You have to pay some tax to cross this gate, and there are several gates in the way. You'll have to pay taxes. Suppose it's the first gate. You have to pay some tax to meet with the king and to tell him about your complaints, about your problem. So pay the tax. And the C1 has more amount of complaints, C2 has less amount of complaints, and that's why soldier tells him that C1, you have to pay more tax, more money as tax. C1 is paying more money because C1 has more complaints to say with the king. Soldier say to a soldier is saying to C2 that you have to pay tax, but your tax amount is lesser than C1 because your complaints are less. But the striking feature is here, less money. And this is not the ordinary money, this is the tax fee. No, we can't tell it tax, we can tell it the fee. Soldier is telling him, C1, that you have to pay some fee to meet with the king and to settle your problems. But the striking feature is that the ratio of this money to the complaints, number of complaints of C1, and ratio of the money paid by C2 as fee to the soldier with respect to and ratio of the number of complaints of C2. Suppose C1 has N1 number of complaints, C2 has N2 number of complaints, then money paid by C1, that is money paid by C1 have to pay M1 money and C2 has to pay M2 money. So M1 money paid by C1 as tax to cross the gate and to meet with the king with respect to number of complaints of C1, that is N1. A striking feature is that these two ratios are same. The amount of money paid by C2 as tax, tax as fee to pass the gate and to meet with the king and share his N2 number of problems. These two ratios are same. And we think that this tells us that whatever be your number of complaints, your fee differs, but the ratio of the fee with the number of complaints to pass the gate through this gate is same. The ratio will be same. Similarly, at another gate, there will be some different ratio, but that ratio is same for number of complaints
for all the visitors.
For both the complainants or visitors to visit the king and say the problems. This is the same thing what we have discussed in terms of potential, that the charges, whatever be the magnitude of the charges, if we take analogous C1 and C2 as the charges and number of complaints as to the magnitude of the charges, then the paid money by C1 or by C2 at the gate will be the potential energy for Q1 or Q2 to pass through that point and to reach the king. And king is representing the plus Q in our analogous thing. So this is the potential. Means potential tells us that in terms of this, if a complainant is going to meet with the king, then he has to pay some money there. If he has not that amount of money, then he has to return. That's the same thing for a small q. If a small q wants to reach to plus q here, then to each and every point it requires a particular amount of potential energy to pass through that point. And the ratio of those two is constant for each and for any type of charge, whatever be the magnitude, that is potential. Here, this ratio is considered to be equal to the potential, and that is constant. Understood? This is the analogous example of the potential. Now I think it's quite clear. Pause it now. See, as I discussed in a part of this lecture or this video, that this q starts from infinity to reach towards plus q, requires energy at this point u1 to pass through this point. This plus q requires u2 energy, and to pass to third point it requires u3 amount of potential energy, and similarly its energy increases towards, and as we know u3 is greater than u2 and u2 is greater than u1, so energy increases towards plus q. And means as plus q is more closer to plus q, this plus q, a smaller plus q, and this capital plus q, as smaller plus q is closer, more and more closer to capital plus q, along its journey, it has to face more resistance. It means that as closer to plus capital Q, plus a small q has to put more energy with itself. And that's a striking feature. It's something like that. It is climbing on hill. Like plus Q starts its journey from a plane where it requires no amount of energy. So U is equals to 0 at infinity, and this plane land is leveled as the infinity point because plus Q requires no amount of energy to travel from here. And as it is climbing on the hill, at 1 it requires less energy, at 2 it requires more energy than U1. Exactly this like situation. And from U2 to U3 it requires more amount of energy, and to reach at plus Q it requires the highest amount of potential energy to reach here. Suppose take it from either direction, in this direction. Again, at this level, if this slope here and here are almost identical, then at this point it requires U1 energy, at this U2 energy, at this U3 energy. So if plus small q from infinity begins its journey to plus capital Q, then by traveling each and every step, it needs more energy to cross that point. And that's a striking feature. It gives a feeling to plus Q that you are climbing a hill. By raising your step, you need more and more energy. As closer you are reaching to plus Q, you require more and more potential energy to feed it. And that's why in electromagnetic world, we define this type of situation as potential spike or potential hill. This is a potential hill or potential spike. Potential spike. And let's see here, if these 2 points are identical, then the potential energy required to pass these 2 points from either direction for Q are equal, and that's why these two have the same potential difference with respect to ground. Similarly, these 2 points have also same potential difference with respect to ground. These 2 points have also the same potential difference with respect to ground. And if I use this as a 3D picture, then there will be a slope like this or slope like this, and these all points have the same potential difference with respect to ground. These all points have the same potential difference with respect to ground. These all points have the same potential difference with respect to ground. And so these all points are equipotential surface because their potential difference with respect to ground are equal.
Wait.
So this is also an equipotential surface, and it is also an equipotential points along the hill, this hill, potential hill or spike.
Wait.
If there are another charges present here, then they can turn they can alter the spike shape. But this is for just 1 plus Q at the top of the spike, and here plus Q trying to climb the point.
Wait. Yeah.
See, here the potential hill or potential spike for the setup when a plus Q is here and a plus small q is making its journey from infinity to passing all these points towards plus Q. Let's see here. This is a hill or spike or mountain, so there will be a slope of this mountain. And that slope is at an angle theta to the plane. And this slope tells us the electric field. For plus Q, electric field is toward. Actually, the slope is in this direction, but the field will be in this direction. I discussed electric field in my last lecture. So here, the slope of this graph, the slope of this spike, these points representing the potential difference from here to here. So, slope of the potential difference gives us electric field. Actually, slope of potential difference is along this. And field for plus Q is out of the chart. I will discuss that thing in electric field lines. So, field of plus Q is always away from it. So, it's opposite to potential, and that's why I put minus sign here. Electric field is the slope of the potential difference from ground to this point, from ground to this point, from ground to this point, but reverse to it. Once again, listen carefully. The slope of this point from the ground is this, but the field lines for plus Q is away from it, and so this is the slope of this point from ground. This is the slope. This is the slope for the third point, for second point, for first point, or for any given point. But field is opposite to it, so I put a minus. So from here we get a relation between electric field and the potential difference, that the electric field is opposite to the slope, to the change in the potential difference. To the change in the potential difference means it's a scalar quantity, it's gradient of the scalar,
Put an arrow over
and
the
is
gradient.
equals to electric field. No need to put an arrow over gradient.
Okay.
That's true. So we find a relation between electric field and potential. So I have explained the potential heel and potential spike, and then I show you what is electric field. In my next video, I'll explain for all these things for the negative charges. What happens if I take a minus plus Q here and the plus small q charge is going from infinity to this. Then we get a potential value. And again, electric field for this charge, for minus Q here, will be opposite to the slope of the valley. So for this, only this now. In next video, I'll explain this. So thanks for watching, everyone. Wait. And if I'm also a student and I'm saying my own views, I try to tell you what is completely different than any other book. I take the book matters, I study books, but I try to share my own views. So if anyone, anywhere, and anywhere from any corner of the world can find any errors in it, then suggest me. I try to improve myself. And if you need any type of help in physics or mathematics, you can call me. You can contact with me, or Instagram, on our Facebook, and on our YouTube channel, Physics Defines the World, and I put my link in the subscription. Okay, thanks for watching. Suggest my errors too, I welcome you. So thanks for watching.